Welcome to the deep dive. These large language models, LLMs, they've really just exploded onto the scene, haven't they?
Oh, absolutely. It feels like one minute they were purely research, the next, they're everywhere.
Powering all sorts of things we use daily.
That's right. Drafting emails, complex reasoning. The versatility is pretty astounding. Their capabilities are just evolving so rapidly.
But, and this is a big but, as they get smarter, they also become absolute resource hogs.
Yeah. It's putting it mildly.
I mean, trying to run one of the big ones on your phone, forget it. The memory they need, the processing power, it's a huge bottleneck.
Exactly. Especially for, things that need to run locally or in real time.
Or on edge hardware, right? Those smaller devices.
Precisely. That computational cost is a real hurdle for getting them into more places where local processing is, well, essential. Think privacy or instant customer service bots or AI on tiny gadgets.
So researchers are obviously trying to tackle this, and one really clever approach is something called post-training quantization, PTQ.
Yeah, PTQ. The idea there is pretty neat. You basically shrink the model's memory size after it's already been trained.
How? By using fewer bits for the numbers inside.
Yeah.
Right, the weights.
Exactly. Instead of the usual, say, 16 bits for these weight values, PTQ maps them down to much lower values, maybe 8 bits, 4 bits, sometimes even less.
And the key is you don't have to do that incredibly expensive retraining process all over again.
Right. Retraining these monsters can take weeks, huge amounts of computing power. So PTQ offers a much faster way to get a smaller model. You can cut the memory footprint in half or even more.
Okay, but there's always a catch, isn't there? When you push that quantization really low, like down to maybe 2 or 3 bits per weight, performance starts to suffer, right? The model just doesn't work as well.
That's the core problem. You get this significant performance drop at those really aggressive low byte rates. It's been well documented.
We want small and efficient, but we obviously can't lose the actual intelligence that makes these models useful. It's a tough balance.
A very delicate balancing act.
Which brings us, finally, to what we're really diving into today. Task-Circuit Quantization, TAC. It's a new mixed precision PTQ method coming out of UNC Chapel Hill.
Right. And the team there is proposing a really fascinating way to handle this trade-off.
Okay, tell me about it. What's the core idea?
Well, the insight behind TTQ is really cool. They're drawing inspiration from this idea that within the huge network of an LLM, there are specific pathways or sets of weights. They call them weight circuits.
Weight circuits, okay.
Yeah, and these circuits are supposedly really critical for specific tasks.
Okay, let's unpack that weight circuits idea a bit. So it's like saying if you want the LLM to be good at, I don't know, answering questions, there's a specific chunk of its internal wiring that's doing most of the heavy lifting for that ability.
That's basically it. And TTQ's big innovation is a method to actually find these crucial circuits for a given task.
Okay, and once they find them.
Once they identify these important circuits, they protect them. They keep those specific weights at a higher precision, like the standard 16-bit.
Ah, I see. While the rest of the weights, the ones deemed less critical for that task,
those get quantized much more aggressively, down to those really low 2 or 3-bit levels.
So it's mixed precision because you're using different bit levels for different weights, some high, some low, based on importance. Maybe we should quickly define mixed precision TACQ. Again, it just means applying quantization after training, but using different bit counts for different parts of the model.
Exactly. It's tailored precision. By keeping those vital circuits intact, TTQ aims to hold on to the task performance.
While still getting that big memory saving overall by squishing the less important stuff.
That's the elegance of it. Minimize the performance hit, maximize the compression.
Now, this idea of important circuits, is that totally new, or does it build on other ideas about how these networks work?
That's a good question. It definitely builds on this growing field looking at functional modularity in neural nets.
Meaning different parts do different jobs.
Kind of, yeah. There's more and more evidence that different sections of these networks specialize. TACQ uses techniques from something called automated circuit discovery to pinpoint these task-relevant weights more precisely.
Okay, automated circuit discovery. So they're trying to automatically map out these important pathways.
Right, and then they condition the quantization based on preserving those pathways.
So how well does it actually work? The results? I heard they're pretty impressive, especially down at those tricky low byte rates.
The results are quite compelling, yeah. Particularly in the 2 and 3-bit range where, like we said, many methods really struggle. Zhao and the team showed TAQ significantly outperforms the current state-of-the-art methods there.
Okay, give me some numbers. This is where it gets really interesting for me.
Well, one standout figure was for the Llama 38B Instruct model. Using THU, they got down to an average byte rate of just 3.1 bits across the whole model.
Wow, that's low.
Very low. And at that rate, they recovered about 96% of the original model's performance on the MMLU benchmark, which is a standard test for language understanding.
96% at 3.1 bits? That's huge. How does that compare?
It was a significant jump over other methods. For instance, they reported a 5.25% absolute improvement over a strong baseline like SPQR in that setup. That's not trivial.
No, definitely not. That feels like a real breakthrough kind of number.
It really highlights how effective their targeted approach is. Getting
Yeah.
that performance with that much compression is, well, it's remarkable.
Any other numbers that stand out?
They also saw really big gains in the even tougher 2-bit regime. Compared to another strong method, Slim LLM, TACQ showed an average improvement of around 14.74%.
Almost 15% better at 2-bit. Okay, that is significant.
Yeah, a very healthy margin. It shows this isn't just a minor tweak.
So it really does seem like finding and protecting those weight circuits is the secret sauce here. It lets them compress hard without losing as much accuracy.
Precisely. It's a clever way around that efficiency versus intelligence trade-off we talked about, especially important if we want these models running everywhere.
All right, let's maybe start to wrap up our deep dive into Task-Circuit Quantization, TACQ. If you had to boil down, what's the single biggest innovation here?
I'd say it's the way it identifies those important weights. It's more sophisticated than just looking at, say, how big a weight is.
Okay.
It considers the estimated impact of quantizing a weight locally, sure, but it also brings in global gradient information.
Global gradient, meaning how much changing that weight affects the model's overall output or error.
Exactly. It gives a broader sense of that weight's importance to the whole system's function. This dual perspective, local impact and global role, lets it make a much more informed choice about which weights really need that 16-bit precision.
So not just looking at the immediate ripple effect, but the weight's contribution to the bigger picture. That makes sense.
Right, and the results back it up. As we discussed, TXU consistently beats other top methods, SPQR, SqueezeLM, SlimLM, especially at those tough 2 and 3-bit levels.
And that wasn't just on one type of task, right?
No, they showed these gains across a real mix. Complex Q&A, math problems, even tricky stuff like text-to-SQL generation.
And across different models, too, like Llama 3 and Qwen 2.5.
Correct, which suggests the technique is pretty generalizable, not just a one-trick pony for a specific model or task.
That nearly 15% average gain over Slim LLM at 2 bits really sticks with me. That feels like a potential step change for practical model compression.
It really does. And another point in its favor is practical efficiency.
How so?
It apparently relies mainly on just one key hyperparameter. Basically, what fraction of weights do you want to classify as these important outliers to keep it 16-bit?
Okay, so simpler to tune than some other methods.
Potentially, yes. Some other approaches need complex searches for the right quantization thresholds for different layers or groups of weights, which can be computationally heavy and time-consuming. A single main knob is much more straightforward.
Yeah, finding those optimal thresholds can be a real pain point, so simpler tuning is a definite plus for real-world use.
And one other fascinating finding they mentioned, TACQ still showed consistent improvements even when they didn't specifically tune it for a particular task beforehand.
Wait, really? So even without focusing on, say, just question-answering circuits, it still performed better?
Apparently so, which kind of hints that the method might be latching onto weights that are just generally important for the model's overall functioning, not strictly task-specific ones.
Huh. That's really interesting. It suggests maybe there's a more fundamental hierarchy of importance within these networks that TTQ is tapping into.
Exactly. It opens up some intriguing possibilities.
So the implications are pretty clear then. Better ways to deploy LLMs on devices with less memory, less power.
Right. Local devices, edge computing, all those scenarios become more feasible.
Plus, maybe creating more efficient, specialized models for specific jobs.
That too. TTQ definitely seems to offer a promising path forward for making these powerful AI models more practical and accessible.
It really does feel like a significant step, focusing on these circuits.
It provides a novel lens, a new way to think about compressing these models effectively.
And it really gets you thinking, doesn't it? If these task-specific, or maybe even generally important circuits exist and are so critical, what else is hiding in there? What other hidden structures or organizational principles might be fundamental to how these incredibly complex systems actually learn, reason, and, well, work? Could figuring that out change not just compression, but our whole understanding? Definitely something to chew on. Thanks for exploring this with me.